So yeah, one more thing before we get into it. The lab schedule. This week we're doing our crystal growth. So that's our at-home lab, week of April 12th. We're here, we've made it. Next week, don't forget about lab next week. We have one more about visual spectroscopy and Beer's law. And then that'll be our last distance lab for the year. So then our 15th, week 15, there will be no lab. We would normally reserve that for checkout. And I think the idea is this is not overburden students right before the final. And so just keep in mind that we've got one more sim lab, and then this becomes a mere memory. Any questions? All right. Okay, crystallization of alum, pure order from pure disorder. So let's talk about what a crystal is first, and then we'll talk about how we're going to make our crystal. So a crystal is a regular lattice of ions. You can have molecular crystals, but today we're talking about alum. So let's just think ions, right? So here's a simple lattice of sodium chloride. It's a solid, but more than just being a solid, it's a very ordered solid. So the ordering is very specific to the substance that makes up the crystal. So each crystal has an individual unit cell. That's the shape of the simplest ordering of our crystal. So for instance, let's just use this single Lego block as a unit cell. So that means that every time I build my crystal lattice, I'm going to be dealing with exact same shape unit cells, and we're going to then build those out. And so this is basically just how you keep track of all of the different ions and making sure that the charges are balanced, right? So there is going to be a regular repeating order to a crystal. And furthermore, the crystal's eventual macro shape has a lot to do with the shape of that unit cell. So here you can see some unit cells for some different ionic species. And so then you can see that you have an extension of the unit cell shape in the overall macro shape of the crystal. So you can have crystals that are cubic and have a cubic shape exactly as they grow on the macro scale. And that's because on the very, very, very atomic scale, the unit cell is cubic. And so it scales out. So when you grow a crystal, one thing that's important to know is it has to start somewhere or nucleate. So a crystal is a very ordered growth of this system, of these cubic, unit cells, unit cells that are then brought out onto the macro scale. And so they have to start someplace. So there's different ways that you can nucleate. We often use a seed crystal, so a very, very small crystal, and then that's where our crystal can grow from. So every crystal is going to need a nucleation site. You're going to say, later on, I'm going to show you a video of crystals just growing kind of randomly in a jar. And you say, well, where's the nucleation site there? Scratches in your glass can work as a nucleation site. Small pieces of dust can act as a nucleation site, although they're not ideal nucleation sites because it's very unlikely that the nucleation shape is going to be exactly the shape of the unit cell. And that's what we want, is this perfect growth. So we are going to start with a nucleation site like this. And then our goal is to add unit cells repeatedly as slowly and carefully as we can, so that then our overall shape of our macro crystal is a reflection of those added very ordered unit cells. And again, you can nucleate crystals that are cubic in shape, and you can have a hexagonal shaped unit cells with hexagonal shaped crystals like emerald here. And so using my Legos as an example, what I want to do is my goal is that if I have these in solution and they're free moving, my goal is to get them to latch up just perfectly, right? And so if I were to kind of put these in a jar and shake them, so their orientation was always changing relative to one another, and then I kind of hit pause to life, I would probably have, something that kind of looks like this. They would not match up in the most efficient way, right? So it takes a lot of coordination. So when we're trying to cool our solution down and we're trying to get this order, the idea is that if we get our kinetic energy to stay as high as possible, then there's a lot of movement until the Legos can find just the perfect orientation, and another one can come and we can start to build our lattice. So the idea is that we want to keep our kinetic energy high, and we want to keep our ions moving in solution until they're able to orient themselves with the growing crystal in just the right way, and that we can build a crystal out. So the difference between a precipitate and a crystal has to do with order. It has to do with making sure that as we are growing our solid, we're doing it in a very, very ordered way, systematically. And so we'll figure out how we want to do that. But our reaction our reaction this week is very simple. It's just the equilibrium between alum in solution, aqueous, and alum solid. This reaction has a negative sign for its enthalpy and a negative sign for its entropy. So if we're just looking at enthalpy, what does it mean for something to have a negative delta H?
It's exothermic?
It gives off heat, right?
Right, exactly. Both correct. It's exothermic. It gives off heat in the direction that we've written it here, right? From left to right. So we can also look at it in this way. We have alum aqueous goes to alum solid plus some heat. And so when we think about Chatelier's principle, if we increase heat, then we are going to drive the equilibrium to the left, because heat is a product of the reaction as written. So when we increase the heat, we're driving the equilibrium towards solution, towards having the alum be in aqueous form. And then as the solution cools and we decrease heat, then we're going to move back towards the solid in the solid direction. So the goal that we're going to have is to make our solution such that at room temperature, there's more alum than should be in solution, but then drive it into solution with heat and then control the descent back to solid form, knowing that because we have the concentration set at a place where it's going to want to crash out, we're going to do that in a very controlled, or we're going to attempt to do it in a very controlled way, so that our pure lattice can start to form and our alum can start to build this big crystal structure rather than just having this powdered precipitate. So let's get into the how we're going to do it. I'm going to show you a few things that I did at home. I first tried kind of just going through the experiment the way that it's written, and that's really what I'm going to show you. My goal was to do two things, was to grow a baseball size alum crystal within a week. That was something my daughter thought I wouldn't be able to do. By the way, a baseball has an average diameter, 73 to 75 millimeters. You want to keep track of that in your mind. And then also I wanted to grow a really pure crystal, and those paths are a little bit different. Not going to need very much, but how you do your experiment, how you execute it can be done in so many different ways. But you're going to need hot water, 100°C water. So a hot plate, a tea kettle, or even just using a microwave will work. The lab manual calls for a hot water bath. You can use a hot water bath and then put another container within that to heat it up without worrying about contamination of your solution. My suggestion is to use the microwave and just a really clean container, and your water, which can be tap water or DI water. Deionized water would just give you a more pure crystal because you have more ions that will disrupt the lattice in tap water. But if you don't have deionized water, tap water will also work without. You'll see all of my experiments here were done with tap water, so it works. You're going to want something to stir with. That's definitely worth thinking about before jumping in, and it has to be reasonable, and it should be something that doesn't have a lot of surface area to lose your product in, right? So some simple stirring thing. I have these skewers for barbecuing that I use as stirrers. You're asked to use a tablespoon. You really don't need a measuring spoon. I have them pictured here, but you really don't need it. And the reason is that you're going to bring your solutions to the solubility point. And that's the most important thing, is to get it right to the point in which it's in solution at a really high temperature, knowing that as it cools down, our alum is going to be forced out of solution. And so more importantly than getting the measurements right, you've got to get a feel for what that looks like and know exactly when to stop adding hot water. Otherwise, what do you think would happen if our solutions are too dilute when they cool down?
It wouldn't come out of the solution.
That's exactly
Not a lot
right.
of it would come out.
That's right. Exactly right, Taylor. Then this is an important point. If we add too much water and you think, it's just extra water, then if at the cool temperature that's still soluble at that concentration level, no matter what you do, no crystals will form. So you have to have it set up such that the concentration at the hot temperature is above the solubility limit at the cold temperature to drive us towards solid. And so, so keep that in mind. So I will show you in the video that I just used a plastic spoon, and I found out that 2 plastic spoons is about 1 tablespoon. So I kept track of how much I was adding just for my own records, but I kept it in the unit of plastic spoons because I'm really just trying to get my solutions right to that limit. And then I did a couple of tests here. So I did 1 tablespoon, which is what it's called for. And then I did twice as much, 2 tablespoons over here to say, am I going to get more crystals or better crystals, or is anything going to benefit me from changing the first step of this experiment by adding more alum here to the first step? So let's take a look at what that first step is going to look like. There's no sound here, so I'm just going to talk over it. If you're using a container that's got a narrow neck, like I have the Erlenmeyer flask, and of course, once you go back into the lab and you're doing this in the lab, and you're using something like an Erlenmeyer flask, then a piece of paper, whey paper normally is what you would use, but you can just take a piece of binder paper as a transferring tool to be able to get your alum in your container. So I kind of just jostle the paper up and down, and that gets the powder moving in. So that's just a little lab technique that you can bring home if you happen to have a container that has a narrow opening. Taylor, did you have a question?
Yeah. Could you use a funnel too, or does that?
You could in the lab. That's not very good lab technique because why? Why do you think?
Could it get stuck on the funnel, or is it?
Yeah, because you're gonna lose in transferring. And so whey paper and even binder paper, it doesn't have a very big affinity. There's not a lot of places for it to get stuck, and there's not a large affinity for the material. And whey paper is a little bit waxy, which makes it even more resistant to things staying on it. Go ahead.
Would parchment work too?
Parchment paper would be even better than binder paper.
Okay.
But so I'm just, I'm just trying to give you as much actual lab advice as possible so that when you guys are all in organic chem labs, that you have that. So we want to try to minimize using any kind of funnel and using something like this so that we limit how much error we introduce. All right, so now I'm doing twice as much, and see, I've just foregone my measuring spoon, and now I just put 4 of my plastic spoons into the mason jar, 2 of my plastic spoons into the Erlenmeyer flask. And so now I have my hot water. And so my stirring sticks, again, this is going to be really important. You get a good view of my arm. And so you can see it's going to make a milky solution. That's what you really want to see, are milky solutions. That means that I haven't added so much water that I'm past the solubility point, even at the high temperature. And so now that I have these milky solutions, the name of the game is slowly adding until it goes clear. So of course, my Erlenmeyer flask went clear sooner because I only put 2 plastic spoons of alum. So what happened when I added more alum? Not much, because I'm bringing it right to the solubility point. So I'm not gaining anything here because I'm going to end up with 2 solutions at the same concentration because of the nature of what we're asked to do here, which is to slowly add hot water until we just make it clear, so that at 100 C, it just is soluble. And you can see it going from that milky white to clear with a very small addition of water. So now we're going to see the crystals grow. This is happening. You'll see timestamps. This is after 1 hour. You're asked to wait 3 to 4 hours. And then here's 2 hours. And so you can see some pretty constant growth and 3 hours. And my argument is right around 3 to 4 hours, there's no benefit to waiting much longer so I think after 3 or 4 hours, you're going to get your seed crystals. And then this is just what they look like afterwards, really quick. So you'll want to just decant out the solutions. You might choose to save those solutions later, so we'll talk about why. But so you can hold off on them. And then I just wanted to show you, based on doubling up the amount of alum that I put in, what kind of seed crystals should I expect to get? And the answer is a ton. I still have seed crystals. I'm still doing alum experiments. Both of these would have given me enough seed crystals to do dozens of experiments. And I ended up just giving them to my daughter's crystal collection. So there is no benefit in increasing past a tablespoon to making seed crystals. Just bring it right to that solubility point, wait 3 to 4 hours, and then you should get crystals that will work well for seeds. Okay, preparing seed crystals. Are there any questions? I'm gonna just double check.
Does the water need to be boiling? Because you said warm water, but
Definitely boiling water, as close to 100 as possible. And I'm going to talk about some other options that we have for doing that more efficiently. But I want to just kind of give this. These are the operations as the instructions really say, with the exception of I'm not using a hot water bath. I'm just keeping my hot water hot on a hot plate and slowly adding it. So it's at 100 C, and I'm adding 100 C as quickly as I can. Especially for...
Is there any way you recommend adding the water, or just like with the,
carefully. Yeah, carefully. So I have, a hot mitt, a couple of hot mitts, and I was holding those. Definitely, this is a great question, and it's one of the reasons. So if we have more hot things in our lab, the more risk that we have of having an accident. And it's really important to talk about this because our labs this week are our homes, and all of our homes are different. I've got 2 kids in my home. People have siblings, they have their own kids, they have other roommates. And so there's a lot of moving pieces, and we want to make sure we're staying safe. So to answer your question, I would use the largest container if I'm heating the water up as possible, because I don't want to have the hot water right near my hand. I want to give some space. So I used the largest beaker that I had, the 1 liter beaker. Now, we're not going to have beakers at our homes, but use a container in which once it's hot, you're able to hold. And if you don't have any hot mitts, some of us are just setting our houses up as adults, use a towel, any kind of towel that you can really, it's not too big, not a beach towel, but like a nice hand towel, and fold it a few times. And then you can bend it over and grab the hot water. And then the most important thing with any lab, and unfortunately it's your glassware, but if something slips, because obviously whenever you're using towels and things like that, your grip becomes not as good. And if something drops like that, it's important to just keep your hands and body away and let it fall and break. Now that is much easier to say when it's our glassware and not the things at home, but just keep in mind that there's very little good that can come from chasing, boiling, breaking glass, and also keep in mind, I can never enforce people to wear lab goggles at home, but But sometimes it's interesting. People think only about about dangerous toxic chemicals and why they need to wear goggles, acid in their eyes. But glass is a really, really dangerous thing. And I've seen people get cut much more than I've seen serious chemical burns in any lab. And so when you have hot things that you risk dropping, safety goggles is not always a bad idea. And then of course, when we're in face-to-face labs, that will be a requirement for this reason exactly. So definitely, if you want to try the double bath, the hot water bath, I recommend that. But you can keep water warm. And it's really easy to keep water warm in the microwave as well. So you can, what I was doing at the end, so I started with the hot plate, but that ended up just becoming more, there was more safety concerns than I needed. So what I ended up using was in the microwave, I have a small Pyrex measuring cup, glass measuring cup. And so I just put DI water in there, put it in the microwave till it was boiling. And then I was able to get it out, grab the handle carefully and distribute my water. Does that answer that question? These are good questions. All I've got is sunglasses.
Yes, thank you.
Snowboarding goggles, that's a good idea. Yeah, anything. This is lower risk. I mean, you are talking about glass falling, breaking, which hopefully no glass breaks for anybody, and then bouncing up at your face. So it's like, I would probably not wear sunglasses. I would probably just go as safely as possible because you don't want any of your safety gear making it less safe for you. But we should always think that we shouldn't just think, hey, water, there's no risk. This was far more dangerous in my kitchen than the cabbage lab based on just what I was dealing with. So, okay, so this is kind of the hardest part. So the next part is now that we have our tiny seed crystals, which are only going to be a, few millimeters in size, you can see them here. We need to find a way to suspend them in our saturated solutions in which we can grow our larger crystals from. And so just pause really quick here. You can see in the hands of my daughter who we were working together on this, and she got so frustrated with it. You'll see my hands come in. And I end up having to speed this video up 20 times, which is the fastest I've ever sped anything up because it took us so long to do this. Keep in mind that a crystal to grow, you need a nucleation site. And ideally, we want to suspend that nucleation site right in the middle of our solution so that our crystal is able to grow unabated in every direction. So that's the idea. So we're going to have some sort of way to suspend our crystal. So here I have some floss. And so this is the technique that I developed, what you're going to see now, which just takes like a pencil or a pen, and then you tie around your floss, your string around the pencil, tie it once and you slide it off. And then you drop your seed crystal and you try to pull it tight around. So you kind of create a little slip knot and then you drop your crystal in and you pull it tight. So this is the way that I devised, but this is a really kind of, it took me a long time to get it. By my 6th or 7th trial with this experiment, I was able to get it pretty quickly. So tweezers, but you'll also see us just using our fingers. So now I've come in because, so also if you have somebody else on hand that can be a second pair of hands for this step, this would be a good idea. You're going to see, I'm going to set up multiple of these because I'm going to do multiple experiments so we can get a little bit more information for ourselves before we kind of open up this conversation. But you can see this kind of slow process of getting the crystal in and then pulling it tight. And then you want to trim up everything. So this is just standard kitchen string. So did I see a hand go up, Elliot?
Yeah, I had a question about forming the seed crystals themselves.
Sure.
If you're to try to make it easier to have a nucleation site, such as the one you're doing right now,
right?
Would it be better to sort of suspend a piece of the string in the solution while you're trying to get the seed crystals so that some may form on that string itself? So then you can just drop that into the new solution?
That's brilliant. That's a really good idea.
I remember doing that with sugar crystals.
Yeah.
Back in the day.
Try that. So if anyone else is catching that, especially I would try that if you have string and not floss. I think floss, it's probably not going to work.
Too
But
smooth, right?
right, but the kitchen string that we're talking about has a lot of surface area on it. And so you might just seed straight onto that. If you just dip the
Oh.
string in plain, is what Elliot's saying. In that first step, when we grew our seed crystals, you just dangle some string in there. You might grow seed crystals on the string, and then you can skip this step. So experimentally, if you choose that, I'm highly trying to encourage people to make some choices and try to understand, you know, predictably, scientifically, this is how I'm going to approach it. And I think it's going to work best if I do it this way. So
Great.
is there any other question?
No, that's it. Thank you.
Yeah, good suggestion. So this takes a while. The floss is even harder because it's so small. So you'll see us moving at 20 times speed, trying to get this crystal in. So warning, this part can be tough. Don't worry if it takes a few attempts. So this is just us showing. My daughter was like, are you putting in a gag reel? And I'm like, it's not. It's just to show students that it's tough. That way, if you're struggling, you're not feeling like, oh, I'm failing at this when it looks so easy. So it's not, it takes a while to get it just right. But you'll see the second one. So here I've finally slowed down the video, which means I finally got it. You can see I'm using a lot of fingers here, trying to get the floss just around it, just right. So it's a little bit of a tricky operation. But once you get it, the crystals hold pretty tight in the floss because it's a little bit stretchy. And so then you'll see sped up how much faster it is to do. Once you start to get it, I think this one just went like nothing because it's a small learning curve. All right, so now I have 3 seed crystals, one that's using kitchen string and then 2 that are using floss, which I predict will be the better string. So I've kind of made that experiment. Okay, and so then finally, and I think I didn't mention this, but when we grew our seed crystals, and this is going to say so in your, in the lab manual, but you're going to keep it uncovered so that you're going to encourage evaporation, and that's going to speed up the crystal growth and try to make it go quick so we get a lot of little crystals. Remember, at the seed crystals, we want a lot of little crystals, and then later we want bigger crystals. So now we grew our seed crystals, so we have to make at least 1 more solution. So 2 saturated solutions, and now we have our seed crystals to dangle in the middle of our solutions. So I'm going to use here test tubes just because I have test tubes. I ended up using mason jars a lot. So you can see I have a few different ways of suspending the crystals in mason jars. Let's see what else. I just used cups. I used a big mason jar eventually. So lots of different things. So don't feel like you need test tubes at all, but I just use them for kind of the video really. So now I'm going to make, so now I have a narrow opening. So I'm going to use that paper technique, or it looks like Lily's going to use that paper technique. And we're making saturated solutions. So the important thing we learned is we really need to make sure we have a lot of alum. So you can see how we just added a lot and have your stir ready. Now you don't have to do 3 of these here. You only need to do 1. And I'm going to show you all 3 running at once. There's no benefit to doing 3 at once unless you're experimenting. I'm changing variables, but you don't need to do it 3 times here. You only need to grow 1 crystal. But you're also allowed, I grew so many by the time I was done because I just had fun with it. So I'm trying to make sure that the solutions are completely clear, going right past, just past that hazy. And now I'm going to suspend and cover quickly. So now I'm acting much faster. Now that I have my hot solutions, I want to get them into the experimental setup as quickly as possible. So my experimental setup is that I have a seed with the string and a seed with the floss, but both of these crystals are being grown exposed to room temperature. And then a third, which is has the floss as the string, or as the for the nucleation of our seed crystal. But now I have wrapped it up in a towel. And so what do you think is going to happen for the solution in which I've wrapped the towel around the solution? Not a trick question.
The heat will leave slowly.
Yeah,
slower.
so we're going to change how we're cooling it down, right? So this is kind of the first hint to how open-ended this project can be, but understanding that once we do everything that I just showed you, now is where the thinking begins. Because now you have to figure out how to get that saturated solution to make a lattice around your seed crystal perfectly. And that's not totally simple. So let's just watch the stop motion go, because it's fun. So you can see the seed crystals growing out. So as Elliot pointed out, you can see all this nucleation happening on the string. So you can actually utilize that fact. Here you can see that it's all growing on the single crystal, but it's starting to get frayed here at the edge. What do you think this fraying is coming from here? Anybody have an idea why this crystal might grow a little bit more jagged? Maybe it's cooling too fast, right? So let's take a look at our, yeah, Sophia.
Oh, no, sorry. I was going to ask what you meant by jagged.
Oh, so I was just seeing, well, I'll show you. Let's just, so I would call this crystal jagged with lots of little edges. And I would call this crystal very smooth, very straight lines, very clear, right? And so what we see is our three crystals. We have all of that little seeding here. On the seed crystal, we've got maybe a nice growth, but really small crystals grown here, probably because we lost a lot of our growth along the string. Our two floss examples were clearly grew the best crystal. And what happened? We grew this crystal at room temperature, so it cooled much faster. And we can see that the crystal is less transparent. That indicates a less ordered lattice. It's larger and it lacks more defined shape. Our crystal that we grew at a slower temperature gradient has a much more defined shape to it. It seems to be growing more ordered and it's much more transparent. You can actually see the floss sticking through in the middle. And so we know that there's much more ordered here. And so I'm going to say that this crystal is my best effort. And so what I'm going to go from here is I'm going to try to grow my baseball sized crystal from this now my seed. And what my plan is, what I planned to do, and you're going to all make your own plans this week, is I was going to replace my solution every day to my jar. And I was going to wrap up my solutions in towels the way that I had done it and not change much anything else. And so this was day one. So this is just after that first growth that we just saw, and I'm going to measure it. Of course, I'm remembering to estimate that one digit. So it's between the lines. So it's 19.05 centimeters to 20.10 centimeters. So I have that estimated digit. So sig figs are one of the only things that you can really bring. So make sure that you get that right and that we have the 2 decimal points there, 1.05 centimeters. So then I place the solution, and now want to point out that at this point I couldn't go back into the to my test tubes. I needed a different container. And so I took a stick, that same skewer, and I tied my floss, actually some duct tape around the stick. And then what that allowed me to do is suspend my crystal, and then I could roll up the string until it was just the right height. And then I put another piece of tape over it. And that allowed me, as I changed jars, to change the height at which my seed crystal was suspended. So I recommend something like that. You want to cover up your solutions. So here I've used just plastic wrap. You could probably use foil. And then I've wrapped everything in a towel. So I repeated this every day, and I just changed the solution with new hot saturated solution once a day. So day 2, I got 1.70 centimeters, and day 3, I got 2.35 centimeters. You can see as my crystal is growing, it's losing its shape and its transparency, because every time I'm adding to my crystal, I'm not going to necessarily be adding exactly to the same lattice, because we have some disconnect in the lattice as it cools each day. And so then that kind of grows, that error in your crystal lattice grows and grows and grows as the crystal grows. So measuring carefully after day 3. So then on day 4, between day 3 or on day 3, I guess, I changed up my procedure a little bit, and I started putting my solutions, my hot saturated solutions, in the microwave. So I would use hot water and get it till it was just about saturated. And then I would put it in the microwave until it went clear. So it'll boil and you'll actually see it in the microwave go clear as the water heats up and the solubility changes. You might have to take it out, stir a little bit. And then what I did is then I added a little bit more alum on top of that, and then microwaved it a little bit more. And because of colligative properties, every time I added salt, I was also increasing the boiling point of the solution. And so because of boiling point elevation. So by incorporating heating and adding a little bit of alum, heating and adding a little bit of alum, I could push the saturation of the solution a little bit further, but I don't recommend going too far, and I'll show you why. So just maybe a little bit more alum, but we don't want to get greedy here. But once I did that, my growth took off a little bit. So now by making the solutions just a little bit hotter when I started the process of growing the crystal and a little bit more saturated, you see it grow to 4.5 centimeters. Day 5, I went to almost 7 centimeters, and then I was out of solution. So one of the problems with trying to grow a big crystal is you need a bigger and bigger jar. You need more solution to cover that crystal, which means you need a larger volume of saturated solution, which means you need more alum. So at this point, I was out of alum for a day 7. So I just went for broke and I left it in for 2 days. And I ended up with this giant seed, this giant alum crystal, which has a diameter in one direction larger than a baseball. So I feel like I accomplished that. And so here we have, this would be the picture that you would turn in, just one picture. You don't have to draw these lines on it, just have a picture and measure it. Really straightforward this week on what we're actually going to be doing. How we get there is a challenge that's up to you. Crystals can be big and crystals can be pure, but rarely both. Why?
Because when you increase the size, it's harder to get them more pure and more arranged.
Right. So whenever we are approaching making a crystal, if we want it to be very large, it's much harder to ensure every single ion pair or group is oriented exactly in its unit cell orientation. And so how do you think we should change our approach if you want a big crystal or a pure crystal? Well, so what would be this trick, do you think, to growing a big crystal based on what I just shared with you and showed you on me growing what I would say is a big crystal?
Saturation.
So somebody said something about saturation. That's good.
More saturated solution.
More saturated, but I told you that I can continue to push my solution saturation higher and higher and higher using that microwave technique, right? But I told you don't get greedy. What do you think will happen if I went, because I can, super duper 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 saturated? What do you think would happen to our crystal growth?
Would it just like instantly become alum?
Yeah, we just have a giant hockey puck. So you can literally push the solubility so much that it just crystallizes into something without shape other than just the container. So that's literally by just pushing the solubility using those colligative properties, I can make a crystal hockey puck. So don't push the solubility too high. I would say the key to making a big crystal is as soon as the crystal stops growing, i.e. as soon as the solution has reached room temperature, getting more solution in. The growth of a large crystal is going to be dictated on the driving force into getting stuff from solution into the solid state on the crystal. So it's really going to be about how much alum we have and how often we choose to change the solution. You don't want to change the solution too soon if it hasn't cooled all the way down because you're throwing away crystal growth. But if I waited 24 hours, because I just decided that, you might have to change your approach. What about a pure crystal? Why do you think the trick is for growing a pure crystal?
just like slow and steady.
Slow and steady, although I will tell you that if you go too slow, and you keep the solution too hot too long, you can actually melt your seed crystal and then nothing grows. So if you see, when you come back to your seed crystal, if you just see a loop, it means that you cooled too slowly and you didn't get it. At some point, you have to have a driving force going from liquid to solid for a crystal to grow. Get creative. So I showed you the stick technique for the hockey puck, right? And then also I have just duct tape and my floss on the top of my mason jar lid. And so that makes it easy to cover it and contain my solution in that way. So how you suspend is going to be unique to your setup. So how do you think, so how are people thinking they're going to heat their solutions? What sounds good for your home? Can I just hear a few people's ideas?
I'd say either microwave or stovetop.
Stovetop. And then what's your good technique for stovetop then? Are you going to use like a kettle? Because depending on what kind of stove, if you have a gas stove, you're probably not going to want to put a piece of glass right on it.
Yeah, so I'd probably use a kettle and then transfer it, and maybe even preheat the glass to keep it from shattering because I don't have Pyrex or anything. But I had a question. If I had enough alum, because I bought like a pretty big bag on Amazon by accident.
Yeah.
And could I do it all in a single pot if I dissolved enough in a solution? And say I use the wooden stick technique,
Mhm.
put the seed crystal on floss or whatever, and then just keep it in that single pot. And when it cools down, add more alum, then heat it back up. That type of deal.
Yeah, and so I talked a little bit about saving the solutions afterwards because there's still alum in those solutions. And so you can reheat that and just put more alum in until you reach that solubility point and keep going. That's what I ended up doing, was I saved everything. And there's sometimes crystals that grow on the bottom of your containers. You can heat those up and get that alum back into solution too. So yeah, you can just keep adding alum. So yeah, I think, and I'm not saying that the hot water bath won't work, but just you're going to want to make sure that you're keeping the bottom water hot and you're just staying safe. So it's just a little bit trickier. Yeah, Sophia, you have a question?
Would you reheat those crystals in the microwave?
Yeah. Yeah, I use the microwave a lot just because of how easy it is. The crystals are going to take a little bit longer because they're at a lower energetic state than the powder. And so it's going to take a little bit longer to get them, but they will go into solution. So yeah, just taking the container, getting your important thing out, patting it dry, and then you just have your thing and you put it in the microwave, heat it up, stir it, heat it up, stir it, and keep working until you have that solution. And then you can add a little bit more alum, make sure it's right on the edge of the solubility point, put your thing back in and put it back in your, wherever it's living in its nest. So yeah, what materials, anybody have an idea for a container that they're going to use that they think, because they don't know how else, what other containers to use? Anybody have anything in there?
Well, I have this little glasses that they were from a dessert from Costco, but they might be too small at the point that the crystal is growing. Like they're like,
Yeah, it really depends. So the first day you shouldn't expect anything more than, so yeah, those will work great. Yeah, that'll be fine. That you'll be able to use that for a while now.
Okay.
Or if you're growing a large crystal. And so yeah, baby food jars. I'm a big fan of recycling and reusing materials. So think about recycling containers in your area that might have those jars, even if you don't have babies at home that eat baby food. How are you going to control the cooling of the solution? Because I came up with a ton of ideas for this and I tried a lot of them and so many of them didn't work. But I had so much fun. And I'm really, a towel is the beginning. I mean, using a towel is one thing. I ended up using, and since we're running out of time, I just want to, but I used a cooler full of towels. I used a slow cooker to control, and water to create a warm bath that then I grew the crystals in a container in that and let that slowly cool. I did double seated baths because water loses its heat much slower than air. And so I was using that to control it. So really just which room it is. Do you have a room that's more in the core of your house that doesn't change its temperature between night and day? Are you putting it in front of a window that cools at night? Thinking about these processes over a series of hours and thinking about all of the variables within your house, within your lab. You put it under your bed, you put it up on top of the refrigerator. Refrigerator stays pretty warm during the day as it radiates off heat as it cools things down. So there's places within your house, use an oven to keep the heat in, to slow the cooling. The other thing is you don't want to agitate these very much. It's probably not a good idea to put your experiments in the trunk of your car and drive around. Crystals really want that slow temperature change and not be bumped around or messed with very much as they grow. So keep that all in mind as you approach this. Really easy data this week. So just the width and length of the largest seed crystal, which I didn't measure my seed crystals. So just remember to measure one of your seed crystals. Also understand that you're going to make more seed crystals than you need. So if you forget, just hang on to your seed crystals until you've submitted everything. I highly recommend saving all your seed crystals until you're totally done with this project. And then just get a measurement of one and a picture of one of those seed crystals. The measurement of your largest crystal. So that's the second part. Remember, it's not necessarily so important how big it is. You're not being graded on its size, but you should record that anyways. Take a picture of it. That's it. That's 4 of the 5 questions are just taking pictures and measuring your crystals. And number 5 is that that table that we learned about in thermodynamics about predicting the Gibbs free energy sign, depending on the signs of delta H and delta S and whether or not they're temperature dependent. This is something that I think that you're familiar with at this point, but your instructors can help you with. It's something that's definitely in Tro's textbook. So I'm not going to belabor it here, but really this is just understanding, the 4 different situations with this equation and what happens to the sign of the Gibbs energy and the spontaneity of the reaction. So really it's very, very low work, but there's so much that you can put your brain into this week. And I really encourage you to take something out of this and to set a goal for yourself and try to achieve it. I ended up having fun. And the reason that I'm bragging so much about this baseball crystal is because it became like a thing in our house for a week. It became a whole event my whole family rallied around. So it's pretty fun and I encourage that. And this is what I'm asking. You don't have to do this. This is not obligated, but every single student, whether I'm your instructor or not, I want to challenge you to beat me. I want you to either grow a bigger crystal or a pure crystal, whichever you decide. And hopefully you make that decision before you go into it. And I want to know how you do. And I want people to challenge themselves and then to show off. So here, without a pun this week, is my email address. Please email me and I would love to see what you're able to do. And I'll put those pictures together and I can hopefully share them with the class before the end of the term. So shoot me an email. I'm just really curious. And I think that here are the target pictures. This is an 8 centimeter big crystal. That's the purest crystal that I could form. Can you do better? So are there any questions?
Yeah, did you make the right one?
Yeah, I made both of those. So this is my pure attempt. That's right here. And then this is my day 6 of my biggest attempt. So, and I failed too. I mean, I had so many times when I didn't cool it down slowly enough, fast enough. And so I had mistakes. So don't be discouraged. Don't think that every time you have to get something perfect, but you definitely can get some really beautiful crystals that really represent the shape of the unit cell lattice that's extrapolated to the macro scale. Any other questions? All right, well, thank you everybody for your attention.
Sorry, Michael, just one question. Do you think if I start tomorrow, I'll have enough time, or should like if I do my crystals today, and then I let them cool, and then tomorrow I play with the getting them bigger? Is that okay?
Perfect, perfect. I think you can do everything in 1 week. Remember, I grew mine in 1 week. It's a baseball size, and I change the water only once a day. You could change the water twice a day and really probably shorten that up to 3 or 4 days worth of work. But have fun with it. I mean, try not to put too much stress on yourself, but I would grow the seed crystals. Make sure you know how to do that. You feel confident about it. And yeah, and then just play during the week. Yeah.
So could we like start it on Wednesday and still have enough time?
Yeah,
Okay.
cool. All right. Well, if there's no other questions, I want to send you all off to class. Enjoy lecture today. And I will be in my lab. You don't necessarily have to show up this week because there's not much to do face-to-face, but I will be there with bells on if you want to chat and talk alum. All right. See you all next week.
Thank you.
Mhm.